New Thinking Aloud is presented by the California Institute for Human Science, a fully accredited university offering distant learning graduate degrees that focus on mind, body, and spirit. The topics that we cover here. We are particularly excited to announce new degrees emphasizing parapsychology and the paranormal. Visit their website at cihs.edu.
Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove, and this is part 2 of our 2-part series on exploring hyperspace. With me is theoretical physicist Saul-Paul Sirag, who has contributed greatly to our understanding of the role of hyperspace in unifying the theories of cosmology with the theories of particle physics, and in Saul-Paul's own case, generating as well a theory of consciousness. Welcome, Saul-Paul.
Good to be here.
It's good to be with you. In part 1 of our 2-part series, we pretty much trace the history of the development of the idea of hyperspace, by which I mean higher dimensions of space or other dimensions of physical space beyond the 3 that we perceive with our senses normally. And we looked at how that idea developed from the ancient Pythagoreans through the Middle Ages and right up to modern times with the development of string theory and superstring theory in physics, and how, as physicists have attempted to unify the various theories that developed about the electromagnetic force, the weak force, the gravitational force, that all of the mathematical unifications of these theories kept evolving into theories that necessarily incorporated additional dimensions of space.
Yes, that's exactly right. The big breakthrough was in 1969 and 1970 when string theory itself was invented, partly in Berkeley at the Lawrence Berkeley Laboratory, and in other places. But the work there was very crucial. They were at that time mostly interested in the strong force because they were producing a tremendous number of new particles in the big particle accelerator they had, which is now not even, it's been decommissioned. It's a very small particle accelerator by present day standards, but in the 50s and 60s it was a rather big one. And they were having a very, very hard time understanding all of these particles, which were all strongly interacting particles, and they were developing many different types of theories. And one very far out theory that was came out of that was string theory, and it solved certain problems, but created many new problems, and wound up not being even a strong force theory at all, and that was discovered that wasn't discovered until actually the 80s.
In other words, string theory was around for a few decades, and people didn't think much of it.
Well, people not only didn't think much of it, they totally put it down, dismissed it as, and only a couple of people, a couple of physicists really were working on it for a good decade. One of those physicists was John Schwartz, who got his PhD at Berkeley. So that's why Berkeley had such a big role in it. It was partly because of John Schwartz, and he was one of the 2 people in the world throughout the 70s who was actively and on string theory. And he was a professor at Caltech at the time, and people down there, probably Feynman, for instance, told him he was crazy to work on such a theory. Because, it didn't have any good predictions. You couldn't do anything with it, and so on. But for some strange reason, he kept working away at it. And the big embarrassment about string theory was that it required, by that time, they developed. It started out being a 26-dimensional theory, and they were able to cut down the dimensions from 20 space-time dimensions we're talking about here, which you have to take seriously if you believe the theory. They were able to cut it down to 10 dimensions by introducing a new symmetry, which they call supersymmetry, and that was a kind of ad hoc symmetry in order to bring in matter particles, because one of the big embarrassments of the first theory was that the first string theory, the 26-dimensional theory, was that it can only deal with force particles. There are two types of particles, force particles and matter particles interact with each other by exchanging force particles. That's one of the basic rules of quantum field theory. And so, of course, you want a theory to deal with both kinds of particles. They're both in the world, after all. And so they introduced supersymmetry and got the dimensions down to 10, and they were hoping that by some new wrinkle they could pull out of the air, like they pulled supersymmetry, they could get it down to 4 dimensions and they'd be okay. But that never happened. We seem to be stuck with 10 dimensions of space-time, and so...
That's, in other words, 1 dimension of time and 9 dimensions of space.
Correct.
As opposed to the 3 that we experience through our senses.
Right.
So that's problematic.
That's problematic. So you can say, well, why can't we walk around in these extra dimensions if they're real? Well, the physicist's answer to that is that the extra dimensions are tiny dimensions. The extra dimensions are little, are inside all of the ordinary dimensions, in effect. And they're inside because they're so tiny. There are different ways of thinking about that, but the way I think about it and the way other physicists think about that is that obviously if you think cosmologically, that is to say about the universe as a whole, which you really have to think about if you're thinking about space-time, and you're including gravity in your theory, and superstring theory has come into its own really only as a theory of gravity. You see, it changed from being a theory of the strong force to being a fundamental theory of gravity. The
strong force is the force that holds the positively charged protons together inside the nucleus of the atom.
Holds them against the repulsion of the electrical force, which is because like charges repel. And so to answer the question how those charges could hold together, they simply invented a new force called the strong force. Then they had to try to understand it beyond that simple, dimple statement, you know. But you get the idea that all these things begin very simply and then get very complicated. So the value of string theory, and the reason so many physicists, hundreds, perhaps 1,000 or more physicists today are working on string theory. It's a very big theory. There's a couple of guys working on it, like, in the early 70s or mid 70s especially. And the reason they're excited about it, of course, is that it's the only theory that we know of that combines general relativity, Einstein's theory of gravity, with quantum mechanics, which is the other big revolutionary theory of the 20th century. And it was considered for a long time the holy grail, still is, of physics, to combine these two theories. And if you want to combine all the forces, including gravity, you have to combine these two fundamental theories. And it's very hard to do because these two theories are conceptually so different. They don't appear to be on speaking terms with one another. And so you have to invent some incredibly overarching theory. And it's not surprising to me that there will be something very new and strange about this overarching theory, because the two theories that are sub-theories now of superstring theory are these two very, very different theories. But that's why we take this 10-dimensional stuff seriously enough to believe that it's real.
Now let me interrupt you for a second, because it seems to me that we can draw an analogy here, that in the early days of geometry, back in the times of Pythagoras and Plato, the idea was developed that the Platonic forms were real, even though they existed only in the mind. Truly, that there was a reality to it. And now we can look back thousands of years later and see the contributions of generations and generations of mathematicians. And now we have a mathematical structure like the original Platonic forms, only it's incredibly, vastly more complex. It incorporates many, many dimensions of space, 9 dimensions of space, 1 dimension of time, as you have mentioned. It seems to explain the most fundamental, pervasive and powerful theories we have of physics. So it's as if there is this huge structure, mental structure, and that it is becoming a powerful reality in our lives.
Yes, there are many different aspects to explore that very issue. I mean, for one thing, from the physics alone, the superstring theory has evolved into. In the 80s, it evolved into 4 or 5 different fundamental superstring theories, and that was an embarrassment to string theory because they all seem to work in one way or another. One would work better for some aspects of physics and some for other aspects of physics. But now, actually, a very recent breakthrough in superstring theory, is going back only to 1994. That's very recent. Now we know that there's an overarching superstring theory, which they call M theory, for membrane magic or mystery, according to the physicist's taste. And this overarching string theory even, has these 5 or 6 different string theories as, in a sense, sub-theories of it. And so the job of the string theorists today is to understand this M theory that they call. Okay, that's on the physics side of it. On the mathematical side of it, some of the basic tricks that the physicists use to do the mathematics of string theory have been grabbed from what they think of as a mathematician's grab bag, except it's not so much a grab bag because there's a tremendous unification of mathematics taking place in mathematics. The kind of unification that occurred when Descartes made a fundamental connection between geometry and algebra, that those kinds of unifications have taken place in mathematics ever since then, but there's a really phenomenal unification is taking place in mathematics that's very difficult to describe without pictures and diagrams and so on. But suffice it to say, one of the most fascinating and mysterious and wonderful things about it is that it entails the Platonic solids playing a fundamental role. And so the mathematicians working on this mathematical unification have kind of become super Platonists. In fact, a Russian mathematician who's played the biggest role perhaps in this unification, a fellow named V.I. Arnold, who's a very great mathematician, as all mathematicians know, he calls this area of mathematics, this unification of many different areas of mathematics, he calls it Platonics.
And I think what you're suggesting is that this new field of Platonics and hyperspace Platonics, if that is likely to affect our lives in the coming decades as much as the equations of Maxwell back in the middle of the 19th century generated vast new realms of technology for the 20th century, things that Maxwell himself couldn't have envisioned. One more point. Though we've talked so much about string theory, and I think we owe it to our viewers to try and explain why is it called string theory. My best guess is, what I gather, is that it's suggesting that all of the fundamental particles of physics are oscillations like a string vibrating through 9 dimensions of space or 10 dimensions of space-time.
Yes, in quantum field theory, which was the basic theory of, which and still is the basic theory of the particles. Remember when I said that there are matter particles and force particles in quantum field theory? The basic matter and force particles are considered geometrical points. They're simply points. Okay, and so when when they change position, in other words, we think of them as tracing out a line in space-time. And we draw things called Feynman diagrams, which are these points tracing out lines and exchanging particles. But you see nothing but lines intersecting lines in a Feynman diagram. And so the string theory idea is to introduce a fundamentally new concept, which is that points aren't the fundamental things. That the fundamental things are little rings, little circles that we call strings. Okay, because they're one-dimensional objects that are a circle. We think a circle is not the disk I'm talking about. I'm talking about the rim of the disk. That's a circle, and it's a one-dimensional object. And
curving
back on itself, just a circle, and that's the fundamental object. And there's only one type of fundamental object. There's not a whole zoo of hundreds and hundreds of particles now. They're just circles. Okay, and what these circles do is they bang into each other and create larger circles. In other words, they join up and then break apart and break and join in a complex dance. And the dance is very complex because they're not doing this in 3 space, but they're doing this in a 9-dimensional space-time. Okay.
Or 10-dimensional space-time.
10-dimensional space-time, I'm sorry. In nine dimensions of space. And so instead of sweeping out lines like you see in these Feynman diagrams, point particles sweeping out lines, we think of these strings in their complicated dance sweeping out surfaces like a very complicated drum head. Okay, and then we think of this we call that the world sheet in string theory rather than the world line that we use in Feynman diagrams. Feynman diagrams consist of world lines in space-time. So now we have in 4-dimensional space-time. So now we have a world sheet in 9-dimensional space-time, but the sheet is vibrating. And it's vibrating in a very complex manner. And these vibrations are the harmonics of the vibrations are the particles, and the fundamental vibration is the graviton. So that's why the theory is fundamentally a theory of gravity. And the graviton is if you try to quantize gravity, you have to have a quantum of gravity, and for years we've called that the graviton, and it's a very strange particle because its spin is 2, unlike other fundamental particles, which are either spin 1/2 or spin 1 in quantum field theory, and it has to be spin 2 because that's the only way gravity particles can facilitate the repulsion of everything, which gravity does.
And I've always been confused because these terms spin 1/2, spin 1, spin 2, to the average person, that's kind of very mysterious. It's hard to visualize what is spin 2.
Well, let me tell you, it's very mysterious to the physicists.
Yeah.
too. Spin is kind of an extra aspect of the particle, and actually to really treat it mathematically correctly, we have to introduce another little space. Actually, we have to introduce an extra 2 dimensions of space. So, in other words, besides space-time, there's a spin space.
Because I have a feeling it's not like a planet spinning on its axis.
It's not like that, but it's related to that. It's related in this way. If you take an electron, which we say is a spin 1/2 particle, okay, and if by saying it's spin 1/2, that tells us that there are 2 possible fundamental spin states that the electron can be in. So we can take a bunch of electrons and we can separate out, but with a certain kind of magnet, we can separate out the one spin type from the other. So suppose we have only particles of what we call spin-up particles, okay? And suppose we send a beam of these spin-up electrons into say, a lead ball or a glass ball, whatever. Lead would be nice, I suppose. Hanging from the ceiling, okay? if we send enough electrons into that lead ball, the lead ball will start rotating. In other words, we think of the ordinary rotation of objects as being made up of jillions and jillions and jillions of quantum spins.
Mm.
So there is a relationship between the ordinary rotation and the quantum idea of spin.
Good.
But like other macroscopic things, we think of this chair being made of jillions of atoms, which are quantum objects. Similarly, if I rotate this chair, then that rotation has to be related to the spin of all the atoms in the chair somehow.
Now let me change gears with you a second, Saul-Paul. Let's
Yeah.
talk about the expansion of the universe for a moment. We were talking about, the Einstein original concept of 4 dimensions of space-time being curved, and since the Big Bang, we have the sense that space itself has been expanding as the universe gets larger and larger over time. You pointed out that the extra 6 dimensions of space that are in string theory never got larger. They stayed.
Right.
It's because originally, when we look at the Big Bang theory, the notion is that it all started out from practically a point or from a very, very small space.
Well, actually, the Big Bang theory says it is a point, which is a problem, of course. It's called a singularity.
Yeah.
And in fact, Hawking and Penrose are famous for proving that you can't get rid of the singularity in the context of standard quantum mechanics and standard general relativity. However,
Well, we can't assume that our viewers know who Hawking and Penrose are. And I don't know that we want to explain it in great detail either, but we're talking about Stephen Hawking and
Roger
Penrose, 2 of the major theorists working in cosmology today.
yes,
Okay.
I'd say so. You see, earlier I said that the 6 extra dimensions are very small dimensions, which explains they're very small. They're, to give you a number, we believe they're about 10 to the minus 33 centimeters in size, which means that they're 33 orders of magnitude smaller than a centimeter, which is about the size of your thumb. Okay, the width of your thumb is about a centimeter, maybe. So think of something 33 orders of magnitude smaller than your thumb. That's the size of these smaller dimensions. We believe something on that order, or maybe 30. Even a proton is much too big to walk around, to move around in these extra dimensions, because the proton is 10 to the minus 13 centimeters in size. So that's 20 orders of magnitude approximately too big, see? So it's far too big. But the proton is made up of quarks, and the quarks, and actually the electrons, are small enough to see the extra dimensions. But it's still a little bit hard to think about these extra dimensions, and my way of thinking about them is to think about them cosmologically. That is to say, to remind ourselves that actually the forces are all unified at the earliest stages of the universe. That's when all the forces really are one force, and at that stage, all the dimensions are the same size. It's not a point now, from this cosmological view of string theory, but it's rather a space, but a very tiny space in one sense, but a very big space in a number of dimensions. It's tiny in centimeters, okay, but it's big in a number of dimensions. And then
like it's 10-dimensional.
It's 10-dimensional, and four of the dimensions get big. The time dimension gets big in the sense that time is very old now. Okay, and space gets big in the sense that, of course, as we know, the universe is tens of billions of light years in size, at least. And so my idea is that, and other physicists have similar ideas, although it's not pushed real strongly yet, is that at the beginning of the Big Bang, all the dimensions are the same size, and some of them get bigger but at the same time the others get smaller, and there's a smallest size down to which the 6 internal dimensions, we call them sometimes, the smallest size to which they can get. At the same time, there's a largest size to which the big dimensions can get, and then the big dimensions collapse down, and then you have another Big Bang, and what you really have is a kind of a seesaw back and forth between these dimensions. And this reminds me very much of actually an ancient Hindu idea of the breath of Brahma, with each expansion and contraction of the universe would be, because the breath of Brahma idea is supposed to take place over incredibly long periods of time.
Eons,
in fact, the Hindu figures that I've come across make it many times longer than 10 billion years. Much longer than that. But the numbers aren't so important as the idea that it's a very long period of time between expansions and contractions, and it is like a breath then.
And we only have about a minute or so left, Saul-Paul, but I'd like to comment briefly, because we've talked about these dimensions being so small, even a proton can't walk around in them. Yet we should say something about consciousness. It may be that our mental experience can occur within these dimensions.
Well, that's exactly right. The 6 internal dimensions are very, very closely related to a geometrical space that I call reflection space, which is actually, in my theory, 7-dimensional.
It could be the analogous to the reflection of ideas itself.
It's analogous to that, and the idea is that physics, actually this comes straight out of the physics in a sense, because in order to, what happens at the particle physics level is that particles change into one another by changing aspects that we call eigenvalues, and mathematically speaking, it's reflections that do this. Reflections in what I call a reflection space.
Now I'm going to have to cut you short because we're going to run out of time here, Saul-Paul. But I do want to share with our viewers the notion that these eigenvalues to which you refer are the experiences, the observations that take place in physics, and in your theory related to what philosophers call quals, which is direct subjective experience itself. And we're out of time. Thanks so much.
Okay.
And thanks for being with us.
Book 3 in the new Thinking Aloud dialogue series is UFOs and UAP, Are We Really Alone? Now available on Amazon.
You can now download a free PDF copy of issue 7 of the New Thinking Aloud magazine, or order a beautiful printed copy.